starting with motion, forces, and energy, then physical quantities and measurement techniques. So let's go. Next page. Let's go to the next page. It's really going to be exciting. So the first topic is what again? Physical quantities and measurement techniques. I'm on the next page. Yeah, that's page 2 of 2. So physical quantities. Please, you can write it down too. And measurement techniques. That's under forces, motion, and energy. Physical quantity. You already have it. You could actually, okay. Physical quantities and measurement techniques. Now, what are physical quantities?
Yes, give me.
Yes.
They have derived units.
Hmm?
They do not have derived units. One of them.
Anyway, quantities are anything you can measure. Measurable parameters. Quantities are measurable parameters. Anything that can be measured. Right?
Yeah.
So I think I can just write it down. We'll not write too much because we need the important things. Quantities are measurable parameters or things that can be measured. Can you mention anything that can be measured? Something, a measurement of something.
Mass.
Good. So mass is a quantity. What other thing?
Weight.
Weight, beautiful. Volume, area, and what have you. So all of these things.
Please can you write it down? I forget.
Oh yes, you'll be written down. So examples are mass. So these are examples. Mass, weight, area, volume, temperature.
Space.
Temperature, space is about volume. This space something occupies. Of course, time, current, voltage, and what have you. Length or distance. Let me just call it distance instead of length. Distance. All right. So, yeah, physical quantities. Now, some of these physical, I'm really happy that we're starting from the foundation. Some of these physical quantities, I will be doing it very effectively. Some of these physical quantities are basic. So we have basic quantities and some are derived. You remember? So what are the basic quantities? Do you remember? You can answer.
Sir,
Yes.
I have a question.
Go ahead, please.
Sir, what's scalar? It's quite
Ye-
not simple as usual.
You have a very interesting question. Scalar is a kind of quantity that has only size, that's magnitude,
Yeah.
without direction.
Vector.
Vector has both size and direction. Just like saying length of a ruler. Nobody is interested in direction. But if I'm talking about weight or force, what direction does weight act? Downwards. It has a value, maybe 20 Newton, but we know it's acting downwards. So it has both size, 20 Newton, and direction downwards. Now, if I'm talking about a force, like a force of 50 Newton, I must indicate the direction the force is acting, whether it is towards me or away from me, or towards you or away from you. So force is a vector quantity because it has both size or magnitude and direction. Did you get that?
No.
Yes. So what I'm saying is, your sister asks about what scalars are. Scalars are quantities. Bless you. Scalars are quantities that have only size, magnitude, without direction. I will write it out in the next page, but I don't want us to miss the line of thought.
Actually, just join.
Scalars are scalars and vectors. That would be part of what we do in details later, but I can just introduce it now. I say scalars are scalar quantities. Scalar quantities are quantities that do what?
Have magnitude or direction.
Quantities that have only magnitude. Magnitude means size, but no direction. In other words, we are not interested in direction, it's just the size. Like the volume of a house, the volume of a box. Nobody is interested in the direction. Did you get that? But like I gave you the example I gave you, a force of 20 Newton, you need to know which direction the force is acting. Because a force of 20 Newton acting towards me is actually different from a force of 20 Newton acting away from me. So we need to know or also know the direction a force is acting. So a force is vector because it has both size and direction. So scalar quantities are quantities that have only magnitude and size but no direction. Examples are what? I just mentioned one. Examples are
Of what?
of vector quantities.
Volume of something.
Volume, mass, time, temperature, including energy,
Work.
and so on. But when we get to vectors, vector quantities have both magnitude and direction.
Length.
No, distance is a scalar because nobody's interested in the direction. So I can add distance there.
Distance.
Yes.
Okay.
How far, we are not interested in the direction. But if I'm talking about displacement, you need to know the direction.
Acceleration.
Acceleration is vector too. So let me just add distance for scalar. Distance, speed, these are all scalars.
Yeah.
But when you come to vector quantities, you have,
Acceleration.
okay, can I just start with, for distance, you have displacement.
So,
Yes.
but in like if you later the time graph,
Like speed time graph or distance time graph.
speed time graph.
Yes. Stuff
Most
like that.
questions. Okay, let's let me say that. When it shall comes to this physics, they say acceleration is something as speed.
Or is what they usually say for distance time graph is speed time graph is the same thing as velocity time graph. What you're talking about is speed and velocity. They
Velocity.
are plotted the same way.
You know this thing.
Yeah, one against the other. So a graph of speed against time will look the same as a graph of velocity against time because velocity is actually speed.
Yeah.
It's just that in velocity we measure it in a specified direction. Okay, so displacement is vector. For distance, which is scalar, you have displacement, which is vector. For speed, which is scalar, you have velocity.
Acceleration is part.
Acceleration is part of vector.
I know.
Good. So velocity is vector, acceleration is vector. Good. I'm listening.
So, but since velocity and speed are basically the same thing,
Yes.
why is speed
scalar and velocity. I'm going to explain it to you now. So acceleration, let me just mention, which picture I think can I mention? Okay, let's look at this displacement. Okay, maybe you can talk about momentum because momentum is also vector. I will show you all this. Now, let me tell you this. If I say, I'm running at a speed of 20 meters per second, is it important to say the direction I'm running? It's not really important. If we say a car is traveling at 20 meters per second, we have an idea of what they're talking about. But if you want to say the car has a velocity of 20 meters per second, you must also talk about the direction. Like the car has a velocity of 20 meters per second traveling towards London or traveling towards Manchester. That's for velocity. Now you are including the direction. But if it is just the size, 20 meters per second, it's only speed you're interested in. Now once you add direction to it, it is a vector. So the difference between scalars and vectors is scalars are only concerned about magnitude, which is size. Vectors include magnitude, which is size, and direction. Can you imagine? I didn't even complete this sentence and I started writing examples. I think I need to zoom this in and write it properly. I need to zoom this in and write it properly. Okay, so please, let's have it fully. Vector quantities have both magnitude and direction, right? Let me use this marker, vector quantities. Are quantities that have both magnitude and remember magnitude means size and direction. In fact, you've already answered usually the first question in a physics quiz paper. You see that around among the first question. Vector quantities are quantities that have both magnitude, size, and direction. And these are examples. All right, back to the general things we were saying about quantities. Remember, quantities are anything you can measure, measurable parameters: mass, weight, area, volume, temperature, time, current, distance. For quantities, we have two broad categories of quantities. We have one we call basic quantities, right? So we have basic quantities. Basic or fundamental are the, as the name implies, the ones that we get others from. Fundamental quantities. We get others from it, from them. You know, all other ones that we get from basic are called derived quantities. Now the basic quantities are many, but the ones you only look at O level for your syllabus are basically three: mass, time, and distance. We can include temperature, what we call luminous intensity. Can you put off that, please?
Put off it.
Can you put it off?
You're fine.
Yes. Luminous intensity. We have amount of substance.
Okay.
I'm on page 2 of 3. Amount of substance, mass, time, distance, temperature, luminous intensity, and current. What's the SI unit of mass?
Kilogram.
Beautiful. You need to know their SI unit. Those SI units are called basic units. SI unit of mass is kilograms. What's the SI unit of time?
Seconds.
Seconds. What's the SI unit of distance?
Chim.
Yes.
Kilometer.
Distance. Distance.
Kilometer per second.
No, distance. You're just measuring a distance. Meter per second is speed.
Meter.
Meter, just meter. What's the SI unit of temperature? You guys are doing great. See how cool these things are. What's the SI unit of temperature?
It's just basic.
What's the SI unit of temperature?
Degree.
No, the SI unit of temperature is actually
Fahrenheit.
Kelvin, right?
That's right.
What's the SI unit of luminous intensity? Don't bother yourself about these ones. You do that when you get to A levels, candela. What's the SI unit of amount of substance? Mole.
Chemistry.
What's the SI unit of current? Ampere. But don't bother yourself about all these other ones. So they are the basic ones. Now when we come to derived, you get them from the basic, derived quantities. Derived quantities. Anything that you can get from any of these other ones, like density. Or let's even start with area. You know, when you want to calculate area, you need to do length times length. You know, length times breadth or length times width. So area is derived from two distances, or length and length. Are you getting what I'm saying? Volume is length times breadth times height. So volume is derived from a length, and another length. Then what about speed? What's the formula for speed?
1 meter per second.
Which is distance over time.
Yes.
Speed is what?
Distance over time.
That means speed is distance over time. That means speed is derived from distance and time. So it's derived. What about
Sorry.
yes.
So you said area, length and length.
Yes, so it's derived from two same basic.
So,
Remember, distance is length. Oh, I told you now.
Oh, okay.
Distance is length. But you I think I need to include mention that distance or length. Length or distance. What about density? What's the formula for density?
Mass times volume.
Mass over volume.
Over volume.
So density is derived quantity from mass, length, and length, and so on. You have other ones like pressure, momentum. Momentum is mass times velocity. Even force, they are all derived quantities. Force is mass times acceleration. Then of course acceleration, and so on. These are derived quantities. I just want us to move further to what we call let's look at this one. I think we need this understanding. Let's look at what we call prefixes we use in measurement. Go to page 4. Abi, that's page 4. Prefixes in metric measurement or metric units. You know what prefixes are in English? What are prefixes?
Things that
You add to stuff, to give it an enhanced meaning, like new. Then you can add new, undo, stuff like that. Disallow. So we have prefixes like that too. You get that? Now, from the basic one, we can have higher values. Let me start with, I will write some that are necessary, some that are not, and then you just work with the ones that you will need. and their symbols and what they mean, and maybe examples. So I will put this thing like this. Prefix. Let's have tera. Giga, mega, kilo. We can even talk about hectare and centi.
So do I need all of this?
You need them. Yes, you do. You need them, but she needs a few of them.
I need them.
Yes. Centi. No, after I'm looking at the higher ones, hectare and deca. Then from the main thing, you will have the smaller units like starting with deci, centi, milli, micro, nano, and pico. All right, so I can draw a line to make it easier. I deliberately left that space so that you can see that that's what divides the higher ones from the lower ones.
The line is not straight again.
It's not coming straight.
No.
Okay. We manage it. We manage it. Okay, tera is times 10 raised to the power 12. So I can talk about meaning, what it means. Maybe first of all, symbol or name. Okay, symbol and then meaning. Maybe examples. Tera means the symbol for tera is capital letter T. Giga is capital letter G. Mega is capital letter M. Kilo is K. Hectare you can use H. Deca you can use DA or deci small letter D, centi small letter C, milli small letter M, micro. Look at micro. Micro is something like this. Then nano small letter N, pico small letter P.
Deca is what DA.
DA. Or D, small letter D and M and A. I think that's how we write it. Like dam.
Small letter D and capital letter A.
No, small letter D and A. Now, meaning tera simply means times 10 raised to the power 12.
Yeah.
Giga times 10 raised to the power 9. Mega times 10 raised to the power 6. Kilo times 10 raised to the power 3. Right? Hectare times 10 raised to the power 2. Deca times 10 raised, that's times 10. Then deci times 10 raised to the power minus 1 or divided by 10 if you like. Divided by 10. This one is divided by 1000 or 10 raised to the power 2. This one is divided by 1000 or 10 raised to the power 3. This one is divided by 10 raised to the power 6. That's micro. This one is divided by 10 raised to the power 9. While this one is divided by 10 raised to the power 12. Okay. So if, for instance, I have 5 tera, whatever, maybe tera ohms, what it means is 5 times 10 raised to the power 12 ohms. That's tremendously large. So I won't have to write about the other one. What about if I have 20 microvolt?
20 divided by 10 to the power minus 6.
Examples. That was 20 divided by 10 to the power minus 6. Okay, so if I have 20 microvolt, that's like 20 divided by 10 to the power 6. Or you can say, okay, let me write it in two different ways. You can say 20 divided by 10 to the power 6, or 20 times 10 to the power minus 6. If you remember your indices.
Oh, yeah.
Is it not?
20 times 10 to the power minus 6.
Let me write it in two different ways so that it will make sense. Okay. Let me write it in two different ways.
Actually, how does it time?
All right, let's see. 20 microvolts. We have 20 times. First of all, let me write it the first way it is. 20 microvolts is like saying 20 divided by 10 raised to the power 6 volts, or you say 20 times 10 raised to the power minus 6, or times 10 raised to the power minus 6, if you like. Did you see that?
Mm-hmm.
It's the same thing. Can we give any other example? If I give you 500 pico, look at this, 500 pico amp. What does it mean?
50 divided by...
I said 500.
500 divided by 12.
500 divided by 10 raised to the power minus 12, right?
Oh,
10 raised to the power 12 pico is 500 divided by 10 raised to the power 10 raised to the power 12
V.
12V, or you say
12 raised to the power minus.
Or times 10 raised to the power that. Okay, or you say this, or times 10 raised to the power 6 because of indices, times 10 to the power minus 12, isn't it? It's the same thing. All right, so that's about, remember what we're looking at is physical quantities and measurement techniques. Now, what are some of the units? Let's even discuss it here. Instrument for measurement, or measuring instruments. What's the instrument we use for measuring length?
Meter rule.
Can have meter rule or tape rule, you know, for length or distance. You have tape rule.
Somebody use.
Pardon?
Mm-hmm.
You have tape rule, meter rule, etc. Then for mass,
So I can't even...
go to page 3 of 4. That's for length. For mass, what do you have?
Scale.
Mass, you have
How is the scale?
I need you to specify the particular scale, maybe beam balance. You understand? Electronic beam balance and all of that. What about time? Stopwatch. What about temperature? Thermometers. For temperature, you use thermometers or thermometer. What about, of course, current? You use ammeter, isn't it? About voltage? Voltmeter, not voltmeter, not voltimeter. Voltmeter. You know, maybe resistance, you can use anometer, and so on. Okay, that's for this. Remember, this is under physical quantities and measuring techniques. Now, I just need to remind you, when you want to measure, you know about measuring at eye level to avoid parallax error, isn't it? Of course, can I just include that if you want to measure volume of liquids, you can use measuring cylinder, isn't it?
Yeah.
Volume of liquid. Let's add that. Volume of liquid. You can use measuring cylinder.
Let's see. Where is the charger?
Measuring cylinder. Okay, so measurement techniques. When you want to measure the volume of a liquid in a measuring cylinder, for instance, or any graduated instrument, you know, assuming you have your measuring cylinder like this, filled with liquid at this level, it usually forms a meniscus. You know what I mean by meniscus? The meniscus is the way the liquid level looks. Look, it forms a concave meniscus, like curving down, maybe with graduations. And so on. Assuming this place is 10, 20, 30, 40, then you have in fact, you know that anytime you record a quantity, you must include its unit. There are two things that must be. Please, this is very important. What I'm saying is very, very important. What I'm saying is very, very important. There are two things you must include when you are recording a quantity: the size and the unit. The unit must be included. Especially, you have to also show that in your workings. When you have, particularly at your final answer, even if you don't show that them in your workings, to simplify your working for simplicity, the final answer should have a unit if it is a quantity that has a unit. For instance, what is the measurement of? Let's zoom it in.
Yeah, can you put yourself?
Okay, good, very good. So what I'm saying is, when you take a measurement, you must include the unit. Let's use this measurement we have here. What's the volume of this water here?
40. No. Wait,
Let me zoom in a bit. Let me zoom out a bit. You need to be careful because this place is 10.
It's not 43.
This place is 10, this is 20. Check the spaces between 10 and 20.
It's 0.4.
Are you sure?
It's 4.
It's not 0 now.
Sorry.
Check the space you have in between 10 and 20. You have 5
4.
marks. 1, 2, 3, 4, 5. Between 10 and 20. So each mark represents what?
1 centimeter.
Are you sure? If each mark represents 1 centimeter, that means look at here will be 10, this other one will be 11, which is not correct. And this will
5.
11, 12, 13, 14, 15, and that's not correct.
Oh, sorry. I didn't. Sorry.
Now the way to get this is this. Somebody has said 4 before. Find the difference between one major marking and the other marking. What's the difference? 10. Okay, that's 20 minus 10. 20 minus 10 gives 10, right? Now divide that by the number of markings, graduations. How many? 5 divided by 5, so that you know the value of one division.
That's 5.
That gives you. It's actually 2.
It's 2.
It's actually 2, so it wasn't 4. The value of each division is 2. So if you have 10, the next one is 12, 14, 16, 18, 20. Did you see that? So this 2 is the value of each division. Value of one division. So this place is 10, 12, 14, 16, 18, 20. You can count like that. So what's the value of this? What's the volume of this water? Let me show you how we can. I want to do it properly so it doesn't get confusing. I want to write it properly so it doesn't get confusing. Let me do it like this and like this, so it doesn't get confusing.
Phosphor.
Okay, which meniscus are you taking?
Phosphor.
Which one are you taking? Is it the lower or the upper meniscus?
The lower one.
So you read the lower meniscus,
Phosphor.
which is here. We're going to read the lower meniscus.
That's phosphor.
You're right, it's 44. So it's 44 centimeters cube. Remember, when you write it, you must write the unit. Now, when you are reading it, it must be read at eye level. This is what I mean by eye level, to avoid parallax error. You know, you position your eye at the same level with the reading. A reading like this is the only correct one. If you read it like this is wrong. As if you put your eye this way, let me show you. Your eye this way will read something like this, which is wrong. If you also put your eye this way, it will read something like this, which is also wrong. So the correct reading is the one in yellow, isn't it?
Mm-hmm.
Which is read at eye level. All of that is to avoid parallax error. So you read at eye level. That's what I'm trying to say. When you're reading, read at eye level. Position your eye. So eye level. To avoid parallax error. So when you read at eye level, the value is 44, isn't it? Because this is 40, the next one is 42, this is 44. So it's actually 44 cm cube. I think that's clear.
Mm-hmm.
All right.